Vector A has a magnitude of 12 meters per second and is pointed east. Vector B has a magnitude of 20 meters per second and is pointed 30 degrees north of west. A, find the magnitude and direction of the sum A plus B, and part B, find the magnitude and direction of the difference A minus B. And there's a hint, does your calculator always give you the right result for inverse tangent? Because maybe in one of these two it doesn't. Looking at this is a classic vector problem, because even though the information is originally given in magnitude and direction, and the results are requested in magnitude and direction, component format is virtually always easier as the intermediate step. So what we're going to be doing here is writing both vector A and vector B in component format, adding them very easily, subtracting them very easily, and then taking those results, which are in component format, and deducing from them the magnitude and direction. The vector A that I'll draw in red has a magnitude of 12 meters per second and is pointed in the direction called east. That picture represents the vector A. When we write the vector A, it's going to have x and y components where x and y are what we call our coordinate system. Now, your professor, when dealing with vectors, may deal with them in a variety of ways. One possibility is that they use the notations with an I carrying a little hat, a J carrying a little hat, and perhaps a K carrying a little hat, meaning the x, y, and z directions. Any quantity wearing a hat simply means that the quantity is a direction. We're used to dealing with units. This is very similar to units in that it's a direction. You also may be familiar with this format, x hat, y hat, and z hat. These say exactly the same thing as I, J, and K hat, only they're a little easier to read because they indicate by name x, y, and z directions. Or finally, something that's a little rarer in a textbook, but is actually easy for students to understand, are the concepts of east hat, north hat, and perpendicular to both of those would be up hat. I'm going to choose the third of these set of possibilities, just because that's how we actually talk about directions. East, north, and up. Now you may respond that west is missing and so is south. Well, west is the negative of east, and south is the negative of north, so really east, north, and up are sufficient to define our three-dimensional coordinate system. So let's write the vector A in that notation. We'll need to ask ourselves two questions, because this is a two-dimensional problem. We'll need to ask ourselves whether the vector A has an east hat component, and whether the vector A has a north hat component. Looking at the vector A, we can see that indeed it does have an east hat component, and when we ask whether that is all of the vector or only a piece of it, we find that that's all of the vector. So 12 meters per second is the east component of vector A, and the north component of vector A is 0. This completes writing vector A in component format. Let's do the same for vector B. The English description of vector B is that it has a magnitude of 20 meters per second and is pointed 30 degrees north of west. The west direction is to the left, and to be north of west means that we are above it in this diagram, and we are above it by an amount 30 degrees. The magnitude of this is 20 meters per second, and we're ready to express the vector B in components. Just like vector A, we're going to have to ask two questions. Does it have an east component? Does it have a north component? And then specify the amounts. Looking at our diagram, clearly vector B is neither entirely along the east-west axis, nor is it along the north-south axis, which means we're going to have to break it into components. The manner by which we do that is we start at the beginning of the vector and we follow one of the axes. Right now I'm headed west until such point as finishing the diagram involves a vector directly along the other coordinate. After this, we're going to be able to easily label the east component and the north component of this vector by looking at the sides that are adjacent and opposite to the 30 degrees. So, asking ourselves once again, does the vector B have an east component? The answer is yes. That component is negative, and it is the piece that is adjacent to the 30-degree angle, meaning that we need to multiply the magnitude of 20 meters per second by the cosine of our angle of 30 degrees. Similarly, we ask ourselves whether the vector B has a north component. The answer is yes. Its north component is positive, and it is a piece of the vector that is opposite to the 30 degrees. Therefore, we will take 20 meters per second times the sine of 30 degrees. Now that both vectors have been written in component format, it's easy for us to continue to either add, subtract, or do anything else we like with these vectors. Let's start with part A. Find the magnitude and direction of the vector A plus B. Well, before we proceed, we need to actually find the vector A plus B. The result will have an east component and a north component, and when we fill in the two amounts, we'll be able to specify the value of the vector A plus B. For its east component, we add the two east components of A and B together with one another, yielding 12 minus 20 meters per second times cosine 30. And when we add the north components of these two vectors, we get 20 sine of 30. We can do the algebra to yield this in a little bit more compact form, with the result negative 5.32 meters per second east and 10 meters per second north. This vector, because of the negative east component, is a little bit west of pointing directly north. To find the magnitude and direction, we need to square add and square root the two components and take the inverse tangent of the vertical divided by the horizontal component. Let's proceed. For the magnitude, we have the square root of the horizontal component squared plus the vertical component squared, which yields 11.33, and the units are meters per second, like both the vector A and B. We recognize that the tangent of the angle of vector A plus B is equal to the ratio of two components. Ask yourself whether it's y over x or x over y. It's y over x. When you take the inverse tangent of this number, your calculator will give you an answer of negative 62 degrees, which points in the fourth quadrant. This is incorrect. We recognize that your calculator will always give you answers in the fourth and first quadrant of the xy plane. However, whenever the thing we are taking an inverse tangent of has a negative x component, we need to take the calculator result and add 180, so that the answer is in fact 118 degrees, which is a little more than 90, meaning if we started in the east direction and went towards north, we would pass north and then go 28 degrees further, just as we expected, a little bit west of the direction north for the vector A plus B. Let's move on to the vector A minus B. To find the magnitude and direction of the vector A minus B, we first need to subtract the two vectors by taking the difference, A component minus B component, in both the east and the north directions. This yields the following result. In the x component, we have 12 plus 20 cos 30, because subtracting a negative is like adding. And in the y component, 0 minus 20 is negative 20 meters per second north. To find the magnitude and direction of this result, we do exactly the same steps as in part A. Plugging in the numbers simplifies the expression to have simply numerical values for the east and north components of this vector, so that we can quickly calculate the magnitude and direction. We calculate the magnitude by calculating the square root of the sum of each component squared, which yields an answer of 35.5 meter per second. As last time, to get the angle theta subscript a minus b, we need to take the inverse tangent of the ratio of y coordinate over x coordinate, except this time, since the x coordinate is positive, our calculator will give us the correct answer on the first try. And that answer is negative 34.3 degrees. Your professor might use IJK rather than east and north. They might use x hat, y hat, z hat, or they might even simply write these results in a table. Whatever. Don't be afraid of the unit vectors, and then the problem is easy.